All right, so you should have already watched Chapter 8, Part 1. This is Chapter 8, Part 2. And so today we're going to be focusing on, in this video, hydration reactions, as well as reduction reactions of alkenes, and epoxidation, and hydroxylation. So let's go ahead and not waste too much time and get started. All right, so first, let's talk about hydration. Now, hydration of alkenes can be done multiple ways. The first way we're going to be looking at it is we're going to be looking at addition of water, because again, it's hydration. So we're thinking about adding water. And so what you'll see when you have a double bond, and I'm going to just draw a simple line structure of ethylene. So it's the same compound. These are the same. These two things that you have, this is the same as what I just drew. And so what you're going to see when you have hydration, and this right here is oxymercuration, but pretty much with hydration, what you're looking at is on the two sides of the double bond. Ultimately, you're going to have an OH being added to one side, and then the hydrogen being added to the other side. And this is the combination total water, right? H2O. And so all hydration reactions, you're adding in hydrogen and an OH group. So the total addition of water is being going on, okay? And so all these hydration reactions, you're going to see that commonality. And so hydration of an alkene is the addition of water to give an alcohol. Reactions take place on treatment of an alkene with water and a strong acid catalyst. So this is actually acid catalyzed hydration that you're seeing right here. All right. So let's look at this is not oxymercuration. I don't know. These titles on these slides sometimes. This is actually acid catalyzed hydration. So let's just talk about that real quick. So the mechanism of acid catalyzed hydration is, again, you need to add water. And so typically you're going to have an acid, and this mechanism is actually showing the hydronium um, um, cation that's going to be your acid as well as your supply of water that you'll see here. So the pi electrons of the double bond is going to be the nucleophilic attack, so that's your nucleophile. And so it's going to attack and take a hydrogen, excuse me. It's going to attack and take a hydrogen from there. And so let's see, you have that there. Now with this is 2-methyl propene. And so I'm going to draw it here real quick so you guys can see this. Matter of fact, let me change my stylus. All right, so you're going to see that here. So whenever you have a mechanism where it's acid catalyzed or an acid that's pushing it through, typically this is going to be a Markovnikov reaction, okay? And a carbocation is going to be formed in these reactions. And so in this reaction, again, this is chapter 7 with Markovnikov. If I have a double bond here, you're going to know that the hydrogen, so let's use different colors. So I have a double bond here. So let's say that the double bond breaks. Let me not redraw the double bond. Double bond breaks. And so now the carbocation has to be formed on one side of this double bond, and then a hydrogen has to be formed on the other side. All right, if you remember Markovnikov's rules, the hydrogen is going to go on the side where it's richer, where there are more hydrogens. And that will allow us to lead to have the more stable carbocation. And so your hydrogen, if you look here, you have 2 hydrogens here, and on the other side, there are no hydrogens. Therefore, on here, you still have your 2 hydrogens that are originally there, but you also have, okay, so this happens like this. You also have that now 3rd hydrogen over here. And because this pi electrons are no longer being shared between the two carbons, but instead the pi electrons that are here went to attack the hydrogen, you're now left with a carbocation on the other side, an empty orbital. So as you see here, you're able to see the hydrogen that was added as on this carbon, which is that one over here I have, which is what I have here. And then on this carbon here, if you look really closely, you're able to see the carbocation there. Okay, so the carbocation right there. All right, so now that the carbocation is there, it's an empty orbital, it's available. The water molecule is going to act as a nucleophile and it's going to attack the carbon that has the cation on there. And so that's where you see this structure here. Now, notice the water molecule attacks it, which leaves a formal charge of +1 on that oxygen. And so because of that, another water molecule can come and deprotonate that water, leaving you with your final product being the alcohol. So just take some time, look at that, pay attention to the movement of the electrons, pay attention to how the arrows move. Remember, the arrows represent the electrons being moved, so it always goes from the nucleophile to the electrophile. So wherever the arrow starts is your nucleophile, and where the arrow ends is your electrophile. All right, so now let's actually go into, so this is just an introduction to what hydration is, and we showed you that's an acid catalyzed, an example of the acid catalyzed hydration. So in the next slide, it should actually be, let me get this deleted. The next slide. It's so funny, for whatever reason, my drawings don't like to be deleted. They're like, no, I'm holding on. But anyways, all right, so the next slide, we're gonna actually see, my computer wants to collaborate with me. What is this? We're gonna actually see oxymercuration, demercuration. Are we seeing it yet? Nope, not yet. Almost. We're getting there. We're getting there. All right, so acid catalyzed hydration of isolated double bonds is uncommon in biological pathways. So what we just saw is very, very uncommon. And there's various reasons. The conditions just are not right as far as whether it's the pH, whether it is the other species there. It's just not common. And so fumarate is hydrated to give malate as one step in a citric acid cycle of food metabolism. And so let's kind of look at that real quick. All right. So fumarate in the presence of water, and you'll notice that the pH is actually very close to neutral. And so since the pH is close to neutral, you're able to see what's going to happen. And so what you have here is slightly a little different. And that's because of the resonance that you actually can see. And so with the resonance, if you notice, let's follow what's happening. These electrons here, let's see if I can do those. These electrons here are being pushed. Let's see. Let's see. Give me a second. I'm trying to get my slides to work. These electrons here are being pushed on here. And then once those electrons have been pushed on there, what you'll notice is it leaves a carbocation. So if you look at this, you'll see that the electrons here are being pushed on here, if you will, okay? And you have a whole resonance situation going on anyways. And so it's going to act a little bit different. Matter of fact, you have resonance pretty much throughout this whole molecule. But anyways, so once you have your electrons there, if you notice that ultimately the oxygen is going to go here. And so if that does push there, the species that you're going to have, and this is just kind of highlighting that one spot, you're going to have your negative charge there, and then your positive charge, if you will, there, which gives it a possibility or a way to be able to create an OH group. And then from there, if you see with an acid here, and so ultimately this negative carbon that's here, this negative carbon that's here, because it's an acid, it can act as a nucleophile and deprotonate that acid, giving you overall malate, okay? And so that's something that you would see, a hydration type of reaction that you would see in biological reactions. Now, for the lab, often a very popular one is oxymercuration, demercuration. And so let's finally go into that actual reaction. All right, so oxymercuration, demercuration is actually a two-step reaction, whereas the first step is actually the oxymercuration. Therefore, you see that you have mercury inside the reaction, all right? And so hence the name oxymercuration as far as the first step. Now, the reaction is initiated by electrophilic addition of mercury ion to the alkene. And this gives an intermediate mercurium ion. Now, this reaction is Markovnikov overall to give you an addition of water. So again, this is important to remember. This reaction is Markovnikov. Now, what also is important about this reaction is, if you remember with the acid catalyzed reaction that we showed first, because a carbocation was formed, that means you can have rearrangement. And again, this is chapter 7. Whenever you have a carbocation, you can have a cation or, you can have a hydride or a methyl shift. Because this compound, or this reaction does not form a carbocation, you will not have any rearrangement. All right, so oxymercuration, demercuration is Markovnikov with no rearrangement. Okay, and so let's look at this. And so the first step, again, you have this mercurium ion that's formed, and then from there you have the addition of an OH group. All right, so this is the oxymercuration part of this reaction. Okay, and then after that, you have another step, your third step, which is going to then remove the mercury. So that's that demercuration step, and it's going to replace it with a hydrogen. All right, and so all three of those steps are needed for the reaction. But the final product that is important to observe and notice is that after all those steps, the same two things are being added, a hydrogen and an OH group. So if you don't remember anything else, remember that. All right, so here goes an example. What is the product of these reactions? And again, you want to remember this is Markovnikov. And so let's go ahead and draw these into stick structures. I am just impartial. I love my stick structures. And so let's do that. So I'm going to go ahead and count my carbons. And then I'm going to draw that 1, 2, 3, 4, 5. Double check 1, 2, 3, 4, 5. In between 4 and 5, I have a double bond. And just so that it's not in the way, I'm going to erase the 4. Oops. The 4 and the 5. All right. So now if I'm looking at this, I'm going to redraw the structure without the double bonds. And then I'm going to look at my 4 and 5 and ask my question is on 4 and 5, how many hydrogens do I have? I'm going to go back to the original structure. Here I have 1 hydrogen, and here I have 2. And you can see that here. This has 2 hydrogens, this has 1. And so the side that has 2 hydrogens already on it is Markovnikov. So that's the side where my other hydrogen is going to be added. Because remember, we're adding H O H2O. And I'm just drawing it this way so you can see how we're adding them separate. All right, so my hydrogen is going to go on that side, and this is the other thing that's going to be added. And so I can simply put it on the other side, and I'm going to put a hydrogen there just so you guys can see that that hydrogen is still there. Where you can see I added a hydrogen on one side and OH. So again, all you have to do is find the double bond, erase the double bond, identify which side has more hydrogen, so you know that's where the hydrogen goes, which side has fewer hydrogen, so the OH goes. If it's a tie, then you're going to have a mixture, and it's not going to really matter which one. You have to give both products. All right. So now let's look at the next one. We have 1, 2, 3, 4, 5 again. 2, 3, 4, 5. 1, 2, 3, 4, 5. Counting carbons is important. On carbon 2, I have another methyl group. And then I have my double bond. I was going to give it a different color just to make it a little snazzy. All right, I have that. So again, I need to know where my hydrogen's going, and I need to know where my OH is going. So I'm going to count hydrogens. This side has 1 hydrogen. The other side doesn't have any hydrogens. How I know that is because carbon has 4 bonds. I count the amount of bonds that are already showing, and then I add hydrogens until I get the total of 4 because it's tetravalent. Also, if I look here, carbon 3 has 1 hydrogen, and carbon 2, you notice there's no hydrogens attached to that. All right. And so now that I know that, I'm going to redraw my structure without the double bonds. And on the side that has more hydrogens on it, I'm going to go ahead and add my hydrogen. And the side that had fewer hydrogens on it, I'm going to go ahead and add my OH. And that is my answer for those 2 problems. Now, if I went a little too fast, go ahead and go back and rewatch that portion. And you can see them there. That's the first answer and the second answer. All right, they did a little flipperoo. Don't get confused. Just notice the structure was flipped, but it's the same structure. Okay. All right. Next we have hydroboration. So this again is adding water, but it's through hydroboration. Now, the mechanism for hydroboration is a bit complex. And so in my office hours or in class, actually, I'll probably go over this mechanism just to kind of drill it in for you guys. But for right now, I'm going to just simply talk about the products. And actually, I'm looking at it. They do kind of break down the mechanism a bit for us. Not pushing the arrows, but you can at least see the intermediates. All right, so the first step that you're going to look at in terms of hydroboration is understand that we're going to be pretty much adding 3 equivalencies of the alkane to the boron. So in the first step, you see that one of the hydrogens is being replaced and that hydrogen is now here. And so this right here is being attached to it. And notice it's going to be attached on the side where there are more hydrogens, okay? So the boron attaches to the side where there's more hydrogens. And this is important because this is an anti-Markovnikov reaction. And so the hydrogen goes on the side where there's fewer. All right, so if I compare this and this side has no hydrogens, this one has one hydrogen. Notice that the hydrogen went on the side where there were fewer hydrogens, and so this is going to lead to our anti-Markovnikov reaction because it's different from the other one where the hydrogen went on the side where there's more. And that's because on the side where there's more hydrogens, where there's more space, the boron is going to attach to that. Okay? And again, this happens actually 3 times, and we're going to show that in the next slide. But overall, you treat it with peroxide and a base, and the boron portion ultimately gets replaced with the OH. And so that's just an oversimplified reaction step showing one of the intermediates or a portion of the intermediate. Just make note that boron has 6 atoms in its valence shell, making boron a very reactive Lewis acid. Okay, if you guys remember, it is a Lewis acid. So this is when I'm saying that it actually happens 3 times. So exactly what happens is you actually have 3 equivalencies to one of these. And so each of these react, and when each of them react, the hydrogen gets placed on the other side. It reacts, hydrogen gets placed, it reacts, hydrogen gets placed. And then the peroxide comes in, and the peroxide is going to cleave each of these off, adding the OH to the side that was on the boron, and that's going to happen 3 times. So you're going to actually end up with 3 equivalent for every boron. And then if you notice with your boron, it's going to actually end up being this. Okay. And that is your answer. All right. So from the peroxide and then the base and the water, you get that. So the net effect of the 2-step hydroboration oxidation sequence is hydration of an alkene double bond. All right. So that's just what the takeaway is. Okay. So just remember with this reaction, what you're getting is an anti-Markovnikov hydration reaction. So at the end of the day, if I have this and I'm doing oxymercuration, if I'm doing hydroboration, I'm going to look, this side has 2 hydrogens, the other side has none. So my answer is going to be OH on the side where there are more hydrogens, and then the hydrogen on the side where there are fewer. So it's the opposite of oxymercuration. And so the important thing about it is when you're reacting and synthesizing compounds, you want to have different ways of doing it. And so you have your hydration, which allows for rearrangement. You have your oxymercuration demercuration, which allows no rearrangement. However, it is still Markovnikov like the hydration one. And then last, you have hydroboration, which does not have rearrangement either, but it is anti-Markovnikov. Also, something I want to point out is that with hydroboration, it is syn addition. So the hydrogen and the oxygen are added to the same side. Okay, it's syn addition. So they're either going to be both on the back or they're going to be both on the front and the end. So the hydrogen and the OH get added to the same side. And that's important, especially when you have a chiral center, you're dealing with a ring, because that's going to determine the stereochemistry. And so if you remember, halogenation was anti-addition. With this one, it's syn addition. All right, and this is explaining why it's syn addition, of how the boron and the hydrogen are being added to it. And the steric crowdedness is just causing it all to be on the same side. And so this non-Markovnikov regional chemistry occurs due to that, as well as the syn addition, okay? And this is just a visual explaining why it is what it is. All right, so what alkene might be used to prepare the following alcohol by hydroboration oxidation. And so if you're looking at this, you're going to want to think backwards. Okay? So I'll give you guys a chance to go ahead and try to do that. So you can pause the video. All right, so I'm assuming that you've done it. And so now I'm going to show you. I see that the OH is attached to this carbon here. And so if I make this a double bond, this side has no hydrogens. Therefore, my OH, this anti-Markovnikov, would be added to this side. And so that would actually just be an easy answer to go into what it is. So let's look at it from the slides. Okay, as you see, going backwards, this is the OH is bonded to the less substituted or the side that has more hydrogens. Anti-Markovnikov. All right, so now we're going to talk about reduction of alkenes using hydrogenation. And hydrogenation is simply the addition of hydrogens to a double bond or triple bond to yield a saturated product. Now, reduction reactions that results in gaining of electron density for carbon caused either by formation between carbon and a less electronegative atom or bond breaking between carbon and a more electronegative atom. So let us look at this. So in this example, we have hydration, where you have your hydrogen gas and your catalyst as well. And notice that the hydrogens are being added syn addition. So they're added on the same side. And so that's important to remember that that hydration typically is syn addition. And how this works is the hydrogens are being absorbed into the catalyst. And so the hydrogens are kind of sitting and floating on this. And so the alkene comes in, if you will, and it is going to kind of float over it, picking up the hydrogen. So right here you have two hydrogens on the two sides of the double bond, right? And then it kind of floats over the catalyst. And as it floats over the catalyst, you see how it picks up that hydrogen there. And then it's still floating and it picks up that second hydrogen before it ultimately kind of leaves as a saturated alkane. All right, so reduction of alkenes, and this is hydration. So catalytic hydration is extremely sensitive to steric environments around the double bond. Okay, very, very they're very, very sensitive. And that's just because of the mechanics of which it is being done. And so if there is steric hindrance, you're going to have syn addition, but it's going to be syn addition, and it's going to favor the bottom face side of it. If you see all of, let's see, get here, all of this part of the reaction, it's just going to be blocky and too build. And so the compound is going to float over it this way, not necessarily this way, because it's steric. So if it's floating this way, this is going to kind of bump into the catalyst, and so it can't reach, the hydrogens can't reach over here. But if it floats this way, there's not a lot of steric hindrance there. And so it's able to float and be more favorable adding your hydrogens on that side, which is what you see here. All right, so this is very important in the food industry. Incomplete hydrogenation results in a partial cis-trans isomerization of a remaining double bond. In biological hydration, biological reduction occurs in two steps. It's reducing agents. You guys, I'm sure you've seen NADPH, those who've taken general biology. And it adds a hydride ion to the double bond to give an anion. And then the anion is protonated by the acid, leading to an overall addition of H plus. And so it's a little bit different biologically, but hydration can happen in the lab as well as in biological processes. And so this is an example of how that can happen. So you see the hydrogen initially is added using NADPH, and then you have this anion being formed, and then from the anion you have an acid that is going to protonate it. And this looks very similar, if you guys remember, from the other reaction that we did with the earlier today. All right. So what products are obtained from catalytic hydration of the following alkenes? Easy thing to do is redraw it without the double bonds, and you have your answer. Now, with that being said, again, if it's a ring, you do want to look at your stereochemistry. So let's go and look at these products. So with the first one, as you can see, you just redrew it and adding hydrogens where you need it to. So here you have no hydrogens. Now you have one hydrogen. And then here you have one hydrogen. And now if you look at it, you have two. Now, if you look here, even though it's a ring, it's not a chiral center. Since it's not a chiral center, it doesn't really matter. Simply redraw the structure without the double bond. All right, so next we're going to talk about oxidation of alkenes, epoxidation and hydroxylation. And with this, it's fairly simple. And so we're going to just kind of look at the big picture. All right, so oxidation reactions that result in a loss of electron density for carbons. So bond formation between carbon and a more electronegative atom, or bond breaking between carbon and a less electronegative atom. Now, alkenes oxidize to give epoxides on treatment with a peroxy acid. And so if you look here, all right, you have an alkene, and this right here is a peroxy acid here. And if you notice, they react with each other with a solvent to form a epoxide. An epoxide is simply a carbon, two carbons that are bonded to one oxygen. And so they're bonded here like that to create that triangular shape. All right, and this right here is just a side product of that because it gave this oxygen away here. So let's look at it again a little bit bigger. So again, your alkene, and it suddenly becomes a peroxide. Epoxide, excuse me. And just to explain, this right here being the peroxy acid, you have a carbon that has, like you remember carboxylic acids, but instead of being just a regular carboxylic acid, you have that extra oxygen in between. And that's where that peroxy acid comes in. So you have a carbon that's bonded with a carbonyl group and then this peroxide portion of it. So peroxy acids transfer an oxygen atom to an alkene with syn stereochemistry. Then you have the treating it with a base with halohydrin leads to elimination of the HX and production of an epoxide. And epoxides undergo an acid catalyzed ring opening reaction with water to create glycols. So remember, if you react a peroxide with an acid catalyzed ring opening reaction, you'll actually get a diol. And so that's with your hydroxylation. So let's look at that. So here, hydroxylation can be carried out directly by treating an alkene with ozonium. So you see the osmium tetroxide. That's this structure here. You can treat an alkene with that, and it automatically is going to, in these two steps, it's going to give you this syn addition diol. Okay, diol meaning 1, 2 with OHs on both of those. All right. And you kind of can see the nature of the structure of why it would be syn addition. It kind of just sits on there and you get this beautiful intermediate with ultimately turning it into the diol. All right, so what product is expected to from the reaction of cis-2-butene with metachloropoxide benzoic acid. So let's draw the structure. So it's butene, but it's cis. Excuse me, I have to change my pen. And you're reacting it with the peroxy acid. And so when you have the peroxy acid, simply what's going to happen is you're going to get a peroxide. I mean, I keep calling them, I apologize, you guys. An epoxide, not a peroxide, an epoxide. So let me erase my stuff and let's see it. Very good, right there. Same thing. An epoxide. And again, it's important to know that, and how I drew it was how it was, that your methyl groups are cis because it's syn addition. And guess what? We got to the end. We got to the end. So the takeaway before we stop is you have acid catalyzed reactions, and these create carbocations. And they are Markovnikov. And you're creating alcohols. Hydration. Then you have oxymercuration, demercuration. Demerc, abbreviated there. These are no rearrangement. I'm just abbreviating, no rearrangement, but because they do not form carbocations, but it is Markovnikov. And again, you're adding OH and H. Then you have hydroboration, which is syn addition, anti-Markovnikov. And you're still adding OH and H. All right, and these were your main reactions here. Then from there, we talked about hydrogenation, where you're adding 2 hydrogens and simply going from an alkene to an alkane. All right, but again, remember, it's syn addition for that as well. And then we talked about epoxidation. And so with our, I'm just going to draw the short side of it, peroxy acid. Simply what's going to happen is you get peroxides. Okay? And then we also did the other reaction when you want to go straight. And then if we treat this, oh, let's not forget that. We treat that with acid catalyzed. That can give us a diol. However, to go straight to a diol, I can have a double bond and I can treat it with this, and it gives me a diol. Again, syn addition. They're added on the same side. All right. And that's just a brief chicken scratch of all that I talked about today. If you want to have a break, let's go ahead and break there. I hope that was beneficial for you. And again, if you have any questions, write them down, put them at the end of the video so that I can answer them when I give you guys your feedback. But that is it.